Let's say you're a kindergarten teacher, and you've been a kindergarten teacher for a few years now. Now, every year you have to administer these two spelling tests, Spelling Test 1 and Spelling Test 2. The first test, which happens in the beginning of the year, is more preliminary, just to see if the kids have a grasp on the material or not. The second test is a big test at the end of the year that you really want to make sure all your students are passing. So over time, you develop this system. You say that after Spelling Test 1, all the kids who are getting above 80% get a gold star, and all the kids who are getting below 80% are getting no gold star. Furthermore, this list of gold star or not gold star is publicly published in the school cafeteria on this list here. So we have all the kids' pictures on the left and whether or not the kid received a gold star or not on the right. So you can imagine all the kids who are getting gold stars feel this pride and accomplishment at showing their peers their achievement here, and all the kids who are not getting a gold star maybe have varying degrees of shame. So now 1 year you're going through the motions again, you're giving Spelling Test 1, Spelling Test 2, and you start wondering, are my gold stars actually helping in terms of boosting students' scores on Spelling Test 2? One naive thing you might try to measure this, which won't really work, is maybe you think at first, okay, after Spelling Test 2, I'll take the mean of the scores of all the students I did give gold stars to after Spelling Test 1. I'll do the same thing here. I'll take the mean of the students who I did not give gold stars to at the end of Spelling Test 1, and I'll just compare the means. So maybe naively you think, oh, I found that mu1, which is the mean here, is bigger than mu2, which is bigger than the mean here, so therefore my gold stars must be helping. You have to ask yourself, why is the mean up here bigger than the mean up here? Is it because my gold stars are helping and boosting their scores? Or is it because the mean of these students with the gold stars are already the students who are better at spelling? Because they only received a gold star if they had high level of spelling ability. Otherwise, they would not have received a gold star. So there's two things going on here. Is it that my gold stars are boosting scores, or is it because the scores are higher because they got a gold star in the first place? But if we look at students just local to the threshold, so here's a threshold of 80, and maybe by just local here, we'll define it as 2 percentage points in either direction. So 82% here, and maybe 78% here. Now, it should kind of make sense that all the students in this range are very similar. What that kind of means is someone who got a 78%, who maybe got one question wrong just by chance, maybe they just didn't happen to study that word or got it wrong by writing the wrong letter, could have gotten something above an 80. By the same logic, someone who got an 82 could have by chance just not gotten one question right. Maybe they got it right just by guessing. That person might have gotten something lower than an 80 if they got that question wrong. Which means that in this interval of 78 to 82 are very similar students who only got the score they did because of some randomness, not really because of any real differences in aptitude. Now, whether or not this is true remains to be determined. Maybe these bounds have to be a lot tighter. Maybe they have to be 79 and 81 or even tighter. Or maybe we can even relax them a bit and still maintain this similar students assumption. That remains to be told. But let's say for now that we do have similar students in the 78 to 82 range. Now, why is this important? This is important because here we have very similar students, but we have very different treatments for either side of them. Between the students 80 and 82, we are handing the gold star. And for the students between 78 and 80, we are, of course, not handing the gold star. So now we can kind of run a randomized experiment without ever really meaning to run a randomized experiment. Because what that means is we have all these similar students between 78 and 82%, and some of them are getting the gold star, and some of them are not getting the gold star. So if we just compare the trends and the patterns of the scores of students in these two buckets, we can really start to tease out the effect of the gold star, because the effect of achievement starts to go away more and more as we consider a narrower and narrower range. So this graph might seem a little bit confusing at first, but we'll go through it step by step. In fact, everything on here we've already talked about. So this graph is plotting on the x-axis S sub 1, which is score on Spelling Test 1, and on the y-axis is S sub 2, which of course is score on the Spelling Test 2 at the end of the year. Now what's going on down here with this C and this epsilon? This C is simply just the cutoff we assign for Spelling Test 1. So in our particular case, the C was 80, right? And this epsilon is that little change, that little window we just discussed. So in our example, it was 2% in either direction, so epsilon will be 2%. And this is 80%. So in fact, these bounds here are 82%, and this is 78%. Okay, so this another name this goes by is local linear regression, and you can see why it's called local linear regression, because we're keeping this linear model very localized. We only care about what happens in these local windows. Now let's keep going. What does this graph mean? These little blue points are all the students, so we're seeing that it's plotting their score on test 1 versus score on test 2, and we see again this is the batch of students who did not get a gold star between 78 and 80%. This is the batch of students who did get a gold star between 80 and 82%. So already we get those gears in our head turning. We're thinking the gold star seems to have some kind of effect, right? Because this batch is clearly distinct from this batch, and furthermore, it's much higher up. They're getting much higher scores. So there seems to be something going on here, right? So just to finish up with the graph, these orange lines are just the line of best fit in this local window. So that means that if we only consider this batch of points down here and try to fit a regression line, this would be the line we get. And same thing, if we consider only this batch of points up here and fit a regression line, that's the orange line we'll get up here. Now let's label a few key values on the graph. There's something interesting going on at the threshold. So at 80%, there seems to be this jump, or you can even call it a discontinuity. Okay, so what's going on at this jump? So maybe we can just tell a little story. We can say, okay, someone's getting 78%. We go a little higher and higher and higher on their S1 score. Of course, that leads to a higher and higher and higher S2 score. So we climb up here, climb up here, climb up here. We get to 80 and bam. They instantly jump from getting this score, which we'll call alpha 1, okay? So it's labeled here on the Y. And they jump instantly from getting alpha 1 to getting this score up here. And we'll label this as alpha 1 plus alpha 2. So it's going to be designated as the original score at 80 plus some kind of extra offset. So alpha 2 is the length of the discontinuity we're seeing here, okay? So what does this kind of mean in terms of a story, colloquially? What this means is if some student gets exactly 80%, okay, and we have the choice whether or not to give them a gold star or not give them a gold star, this alpha 2 is measuring their increase in score instantly from getting that gold star. So that means if we don't give them a gold star, they'll likely stay down here and get something around alpha 1 on their spelling test 2. If we do give them a gold star, then they instantly jump up from alpha 1 and they jump alpha 2 points and get up to alpha 1 plus alpha 2 on their spelling test 2. Okay, so this is one key way to measure our initial question, which is how can we measure the effect of our gold stars on student performance for spelling test 2. One way to measure it is alpha 2. So something you might have also noticed about these two lines is that their slopes are pretty different. If the slope here is beta 1, okay, and the slope here is beta 1 plus beta 2, again, we're expressing it as the initial slope plus some extra bit, and we can see that beta 2 will be positive since the slope here, we can kind of draw it. The slope here kind of follows this pattern, and the slope here kind of follows this pattern, so we can see that this is clearly steeper than this one here. But now, what is the interpretation of this slope? Well, think about it. Let's think about it a little bit. We can see that going from C minus epsilon, so going from 78% to 80%, that's an increase of epsilon, or 2% in our case. We see that the student score is increasing by beta 1 epsilon for these batch of students down here who are not getting a gold star. So just to reiterate that, we see that a increase of epsilon in your S1 score leads to an increase in your S2 score of beta 1 epsilon, right? Because that's how slopes work, rise over run. And this is true for the no gold star kids down here. Now, what's the story for these gold star kids up here? We see that an increase of epsilon, again, we see that 80 to 82 is still this epsilon 2%. Increase of epsilon leads to an increase of, again, we use the slope, so beta 1 epsilon plus beta 2 epsilon in terms of your S2 score. This is a very, very good thing to know because we see that from this piece of knowledge down here, we see that an increase in your S1 score of epsilon leads to an increase in your S2 score of beta 1 epsilon. And that's just by your achievement alone, right? So we can kind of label this as your achievement. Where is this beta 2 epsilon piece coming from? Well, it must be coming from the only other change that happens between this group of students and this group of students, which is the gold star itself. So we see that if you're getting a gold star, then that affects you better and better and better the higher score you have on your spelling test 1. What that means is that if you're getting just above the threshold, you're getting like an 80.5% on your spelling test 1, of course you get the gold star, but it's not going to boost your score as much. It's not going to lead to as much of an increase in your S2 score as someone who's getting closer to the higher end of this cutoff, something like 81.5%, okay? And we see that just by this beta 2 epsilon term. So now the very last thing we might want to do is to figure out some kind of mathematical model to model these two relationships, and it seems a little bit tough at first, there's so much going on, but really we've written out all the important factors and we just have to fill in the equation now. In fact, what's the model for this lower part? The model for this lower part is simply given by S2 is equal to alpha 1 plus S1 minus C beta 1. Can we confirm this? Well, if we plug in S1 is equal to C, which corresponds to the threshold right here, this lower bit goes away, and we just have S2 is equal to alpha 1. In fact, that's true. If we plug this in here, we see that we have alpha 1 here. And of course, the slope we've established is beta 1. So this is the correct model for this bit of the graph. What is the correct model for the right-hand bit of the graph? You see that S2 is equal to alpha 1 plus alpha 2 plus beta 1 plus beta 2, and then we put the S1 minus C here. Is this true? Well, we see if we plug in S1 is equal to C, again at the threshold, we see that this lower bit goes away and we just get alpha 1 plus alpha 2, which is established. And of course, the slope is beta 1 plus beta 2, as we assumed, right? So these are the two equations, and we can actually fit this into one equation. We just have to define this simple variable delta, which is simply 1 if S1 is greater than or equal to C, which is 80 in our case, and 0 if S1 is less than C. So basically the value of this variable is binary and is determined by which side of the cutoff you're on. That's all that's saying. Now using this simple variable, we can compactly take these two equations and put them into one equation. Why is this representing both our equations? Well, we can just see what happens when we plug in delta when S1 is less than C. So if we're on the no gold star side of the cutoff, then we see that delta will be 0. So this beta 2 term and this alpha 2 term will go away and will reduce to this case. Now, if we're on the right side of the cutoff, which means we did give a gold star, then we have delta equals 1, right? So we keep that we have the alpha 2 term and the beta 2 term, and we see we reduce to this equation here, which models the right-hand side of the line. And to answer our initial question, really pull it back to what this all means, the key two values we're looking at to see if our gold star program had any effect will be this alpha 2 here and this beta 2 here. And just to reiterate, what do these each mean again? Well, alpha 2 can be thought of as this instantaneous jump, this discontinuity jump from giving someone just on the cutoff the gold star versus not giving them the gold star. This is how much we increase. And this beta 2 can be thought of as kind of the gradual increase that comes from getting the gold star for people who are on the right side of the cutoff. Think about the applications of this framework. For example, here we use it for gold star for kindergartners. You can easily use it for something like does a scholarship affect a student's GPA? Of course, this is a good framework for this because to get the scholarship in the first place, students have to have a certain level of academic rigor already, so it can be difficult to tease out that underlying academic rigor from the effect of the scholarship. So the key insight you want to take away from regression discontinuity design is that considering a very, very small range of people or observations around the cutoff, we can kind of assume that all these range of people are the same. This is a big assumption, right? But it's a good assumption to make that all these people within these windows are similar. And some of them are getting the treatment and some of them are not getting the treatment. So using this kind of methodology, we can tease out the effects of that treatment, which might be muddled with the effects of the inherent differences in these two groups. So that's regression discontinuity design, has tons of applications in social sciences and hard sciences and etc. So until next time.